So welcome the participants again to the second lecture of this webinar, the Standard Model and Beyond. And for the second lecture, we have Professor Rajesh Gopakumar with us from ICTS Bangalore. The topic being the quest for quantum space-time. So space and time together constitute one of the most basic elements of physical reality. Since Einstein, space-time has become an active participant in the dynamics of the gravitational force. However, our notion of a quantum space-time is still rudimentary. String theory, building upon hints provided from the physics of black holes, seems to be suggesting a very novel holographic picture of what quantum space-time might be. This relies on some very surprising connections of gravity with the quantum field theories, which provide the framework for the description of the other fundamental interactions of nature. In this talk, he will be trying to convey some of the flavors of these connections as well as their significance. So we have today Professor Rajesh Gopakumar with us. Professor Rajesh did his undergrad in physics from IIT Kanpur and then went to do his PhD at Princeton. After being a research associate at Harvard University, he moved to Harishchandra Research Institute in 2001 as associate professor and then professor. He was also a visiting long-term member at the Institute for Advanced Study Princeton from 2001 to 2004. He is the recipient of ICTP Prize in honor of G.C. Wick and S.S. Bhatnagar Award in 2009, the Swarna Jayanti Fellowship in 2006, the J.C. Bose Fellowship in 2015, and the G.D. Perola Prize in 2013, and the TWAS Prize in the Physical Sciences in 2013. He is also a fellow of the Indian Academy of Sciences, the Indian National Science Academy, and the National Academy of Sciences, India. He was elected fellow of the World Academy of Sciences in 2015. He is the founding member, he is one of the founding members of the Global Young Academy. Professor Gopakumar's interests are in theoretical physics, primarily at the intersection of quantum field theory and string theory. So with this introduction, I request Professor Gopakumar to please entitle the audience with the idea of quantum space-time and how the physicists go about it. So I request Professor Gopakumar.
Thank you, Atri, for the invitation, and it is good to see so many young people here for this virtual series of talks on different aspects beyond the standard model and so on. So you just heard Shrirup talk about the standard model of particle physics, which describes most of the fundamental interactions of nature, everything essentially except gravity. And you heard some of the puzzles there, so that is to tell you that the physics is still open-ended. Similarly, my task will be to tell you something about the force of gravity and the puzzles there, and what are the things that people are currently pursuing in that direction. So I've sort of framed this as a kind of since you people are at least much closer to the Himalayas than I am. So this is, if you wish, it is like if you went on a trek to the Himalayas and someone showed you some snapshots from it, it will be a bit like that. So hopefully it will just capture some of the grandeur of the subject and the very novel views that you can see if you go on this trek. So I hope this will encourage some of you to make that journey. So let me start by saying a few words of sort of general philosophy. So this is something all of you, I'm sure, have thought about. What is physics and what is the quest of fundamental physics? So ultimately, physical laws are ways of trying to understand the regularities and underlying patterns of nature. And quite remarkably, from the time that people started doing this, they have been able to capture many elements of these regularities in precise mathematical terms. And that's something quite remarkable about the universe that we have around us. And moreover, what is even more, I mean, continues to be remarkable is that even as we widen the scope of the laws from our daily experience to regimes which are far removed from our daily experience, this way of being able to describe nature in precise mathematical terms has continued to give us great insights. And as you heard from Shrirup, even when you go to extremely tiny distances, you are able to check these laws, experimentally verify them, and match them with the predictions that the mathematical laws give you. So we start, of course, from laws which about things around us. When we start learning physics in school, we start with things maybe like Archimedes' law for things floating, or the lever, or maybe about then we start learning a little bit about motion and how things fall, etc. And there are simple laws, but then these are things which happen at maybe the scales that we are familiar with. But by now we have enlarged our window into the universe in many directions. And you just heard about one of these frontiers. So in some sense, if you wish, there are three frontiers. I mean, in some very loose, simplistic way of talking, there are three frontiers of fundamental physics. You can call them the very small, about which you just heard, the very large, about which I'll tell you a little bit, and in fact, the thing that we will talk about will connect the very large with the very small in some ways. And then there is the very complex, about very complex systems and their laws, which I will not have much to say about, but perhaps also in some ways is a very exciting frontier. So as I said, our quest here will be something which will start from the very large, but we'll see that it also has something to do with the very small, the things that you just heard about. So continuing with that Himalayan analogy, let me just say that 20th century theoretical physics has had sort of two peaks, or essentially stands on two pillars. These are general theory of relativity and quantum field theory, and it's abbreviated as I've shown. So general theory of relativity, as we will just discuss, is what has given us a very successful theory of the cosmos and its evolution on the largest scales. And I think you will hear more of that in the next lecture by Rishi Khatri. But I will talk more about the more theoretical aspects, and he will probably describe much more in detail about the success of the theory, the so-called standard model of cosmology. And quantum field theory, as you have just heard, has brilliantly captured the physics at the very smallest length scales that we can probe at things like the Large Hadron Collider and so on. And as you will also hear tomorrow, in many of the other systems of neutrinos, etc. But as I said, I will focus on gravity. In some ways, gravity is the most common force, I mean, the thing that all of us experience immediately. I think a small child, as soon as he or she starts to walk, immediately gets to know the force of gravity when he or she falls, and realizes that when you throw something, it comes down. So gravity is something that you are, that everyone, so to say, encounters very immediately, unlike, say, the strong interactions or the weak interactions, or even electromagnetic, which is now more common, but at some point was also a very esoteric interaction. And gravity also has the sort of status of being the force for which the first universal law was kind of proposed. And this was Isaac Newton, as you all know, who proposed the universal law of the inverse square law of force between two objects of masses m1 and m2 separated by a distance r. and there's an attractive force between them. So it's along the radial direction, pointing in the direction between the objects. And there's this constant G, Newton's constant of gravitation, which measures the strength of that interaction. So it's universal in the sense that Isaac Newton proposed that this law holds not only on Earth for the force of gravity that the bodies on Earth feel, but it also determines the force of the, the moon is held to the Earth by the force of gravity between the Earth and the moon, and the sun and the Earth are sort of, and all the other planets are held together by this force, and so on, the comets, etc. So Newton applied it to a much wider domain. He immediately opened up the domain of physics from the merely terrestrial to at least the planetary scale. And even now, this Newton's law is what space scientists use, the people at ISRO, when they are calculating the trajectory of Mangalyaan or Chandrayaan as they are sending it. They are using Newton's laws because it is a very accurate description for the force of gravity, for describing the motion of planets. By the way, speaking of which, just a fact I wanted to, those of you who are here, who have clear skies, on December 21st, please go out and look into the western sky. You will see Jupiter and Saturn very close in the sky to each other. It's probably one of the closest in the last 500 years. They will be separated by less than 1/10 of a degree, and they're very bright and visible. In fact, even now from Bangalore, I can see it very clearly every day when there are no clouds. So maybe you will see it in this thing. So anyway, that's a small aside. On December 21st, you will see it really at its closest. So in any case, Newton's laws also, though he expected them to be universal, holding everywhere, not only in our solar system. I mean, he didn't really know of other solar systems and so on, but he expected it to be universal. But what people have realized is that this law also has a certain range of validity. And this is very important as physicists to understand that every natural law that physicists propose is valid in a certain domain. And beyond that domain, the laws break down. And there may be different sets of circumstances under which the laws break down. And that's what happens to Newton's law, and we will see later to Einstein's theory and so on. But it is very important because this expanding of domain of validity, when you go to the larger and larger scales or smaller and smaller scales, there will always be this thing. A very successful law in a certain domain will eventually in some sense break down, and there will be another law that replaces it. So Newton's law breaks down under two different sets of extreme circumstances. So that's what I want to emphasize right now. Because you have all studied Newton's laws, but perhaps no one has emphasized this to you, that Newton's laws are not applicable when objects move very fast. So example, there are things called pulsars, which rotate at very high frequencies, and therefore the velocities on its surface are comparable to the speed of light. And then Newton's laws actually are not applicable to the gravity around such an object. And so pulsars are one object, but one such object, and we'll encounter others such as this. So that's one, if you wish, edge of your, one boundary of your, where the description breaks down, when things move very fast. And when I mean very fast compared to the speed of light. That's the ultimate velocity in nature. And things which are not, which are moving at a very small fraction of the speed of light, like in the solar system, you can still apply Newton's gravity laws very well. The other place where Newton's laws fail is when the density becomes very large. And this happens, for instance, at the center of galaxies, and later we will see in very heavy stars and so on. So when the densities are in some sense large, you will you also find that Newton's laws break down. So we will come back to this soon. So what Einstein did is he succeeded in overcoming these limitations, at least in a partial way. And we will see why it is partial. So this is what Einsteinian gravity, his description of gravity enlarged the Newtonian description by firstly making it applicable at even very high velocities, what are called relativistic velocities, comparable to the speed of light. And it also holds for moderately high densities. For instance, like in neutron stars, they are one of the most dense objects in the universe. You might have heard a teaspoonful of neutron star material can weigh as much as the Earth. So these are extremely high from our point of view, but they are still, in some sense, moderately high from what physicists have learned. And but Einstein's theory is successful in describing at such moderately high densities. But one thing I want to emphasize, even though I won't have time to really describe Einstein's theory, you can see Einstein writing down at least the simplest version of his equations on that blackboard. I won't be able to explain that to you, but what I wanted to emphasize, one general aspect, is that he did not overcome these limitations that I mentioned, these two limitations on velocities and densities, by just changing Newton's law by a little amount here and there. You might have thought, oh, okay, you might have to add some extra terms to that Newton's law that I showed you a couple of slides ago. No, it doesn't work like that. In fact, he accomplished this by changing the whole framework of describing gravity. So it was a kind of an overhauling. And what he did was was truly quite radical, because he tied up the description of gravity with something at first sight seems to be apparently unrelated, which is about the geometry of space and time. Now, space and time, like I said in my abstract that R3 read, are things that you kind of see as they are very basic elements of our reality, but it's something that is just a background normally for us. Yes, we move in this space, we go from this room to that room, we are quarantined in this house right now and for God knows how many months, but we think of these as some intervals that we are inside, but we do not think of these as actual actors in some sense. We don't think of them as participants in all the physical events that we are used to describing or seeing. We think of space and time as a stage on which all the events happen. It's like a drama is happening and there's a stage, but the stage is not an actor in the drama. What Einstein changed was that notion that the stage in some sense became a participant, and it becomes a participant because it responds to whatever is on the stage. It responds to the contents in the space and time. So it's as if there is some drama going on and you have some new high-tech stage in which the stage starts lighting up depending on the moods of the people that are there, and kind of even maybe changes shape and changes the background. Maybe you can have stages like that these days, but that's the sort of thing that Einstein did by changing the nature of the way in which you viewed space and time. So it was not some fixed backdrop, it is an active participant. And so what he did was to sort of say that space and time, as I said, respond to the things inside them, and the geometry of that space and time reflect that, reflect the objects in it. And this is a kind of a crude cartoon of that, which shows that if you have some heavy object like the Earth, then the space-time around it is somehow distorted. And this curvature is to be taken only in some more abstract sense. You don't actually see a hole like that, but the geometry that describes the space-time around the Earth has a distortion which is somewhat what this thing is capturing, and therefore an object like a satellite going around the Earth, instead of thinking of it as subject to Newton's laws with this 1/r² force, Einstein said you can actually view it as this satellite moving in this geometry, and because the geometry is curved, the satellite moves in a curved trajectory, and that's actually the more accurate description as one learns when one looks at more extreme situations. So Einstein's theory, as I said, because the whole view on gravity changed and was in terms of geometry, it was in a way framed in a very different mathematical language compared to Newton. So it was framed in terms of this object called a metric. A metric is the mathematical term which gives you a way to measure distances, as well as a way to measure the curvature of any space, or generally space-time. So by taking distances are sort of proportional to this metric, and so therefore they can vary from point to point. That's what the dependence on x and t says. And the derivatives of this metric give you a measure of the curvature, how much the space-time is distorted, like in that picture I showed you. So Einstein's equations are equations for this object called the metric, and it tells you how this metric is determined in terms of the matter and the energy that is there in the space-time. So that's essentially the physical content of the Einstein's equation, but you have to learn a certain amount of mathematics of curved space-time geometry, so-called Riemannian geometry, to be able to understand the actual equations. So I won't do that here. But what is very striking, and every time, for instance, I used to teach general relativity to graduate students and undergraduate students, what was very striking was the way in which this complicated mathematical framework of Riemannian geometry and Einstein's equations reduces at very low densities and velocities back to Newton's law, the same law that I wrote for you earlier. So that's the remarkable thing, and that's something you should keep in mind, that if one is generalizing and expanding one's domain of description of nature, then whatever that generalization is, you have to, first and foremost, it has to reduce to the generalizations that when you go to the appropriate regime of in this case, low densities and velocities, it should reduce to the old description that you're trying to generalize. It doesn't make sense to make some generalization which has nothing to do with what is already known, understood, measured, tested, so on. So this was, of course, this is a very crucial test, but it's just remarkable how from this very different framework, the same Newton's laws emerge ultimately when you look at this low densities and velocities. But then these equations tell you, if you don't have low densities, if you don't have low velocities, how do you describe the motion? And the Einstein's equations give you a precise way to do that. And you see deviations from Newton's laws. In fact, even in the solar system, there is a tiny deviation in the orbit of Mercury, which people had measured but had not really understood what its origin fully was. And Einstein's one of the first successes was that he could predict that it is due to Mercury moving around in this curved space-time of the sun, the trajectory of Mercury would appear to, so to say, precess at exactly the right amount that was predicted by his theory. So that was an early success, but now we understand Einstein's theory has actually been tested in very many domains. And in fact, You've heard this year's Nobel Prize in Physics, and some years ago, I'll come to some of those things. They're all been for the tests of Einstein's theory in describing the universe and its evolution at the very largest scales that we have currently seen. And the very largest scales, and you'll hear more about this in the next talk, are about 1 million times the size of the Milky Way. The Milky Way itself is our galaxy, and everything that we see, except perhaps the Andromeda galaxy, everything you see with the naked eye is essentially in the Milky Way, in the sky out there. But the universe is, of course, much, much bigger. The Milky Way is just a small galaxy and the local cluster of galaxies, and that's part of bigger clusters and hyperclusters, all the way to 1 million times the size of the Milky Way. We have sort of mapped out the universe, and Einstein's theory gives a very good description of the way the universe evolved to that state, starting from an early Big Bang. But so you can say that, oh, okay, so Einstein's theory is really great. It is marvelous. It has given us this evolution all the way to the largest scales of the universe. So we are now done. I guess this is the most you can explore. So maybe that's the end of the story for gravity. But no, that's not true. And fortunately or excitingly for us, that there are puzzles that Einstein's theory now throws up. And that's what I want to turn to next. So Einstein's theory also has limitations. Actually, it's very interesting. All theories, in some sense, kind of, at some level, at some point you see that they can eventually will break down. And Einstein's theory, in fact, even theoretically, you realize that it has to break down at some point because again, it happens under two sets of limiting circumstances. As you try to enlarge the scope, if you try to push Einstein's theory also to its limits, you will reach two sets of limits which are where the theory breaks down. One is when distances are very, very small, what is called a Planck distance. You heard in the last talk, you heard about the Planck mass. There's a corresponding distance you can write, and that is a very small distance. That's a very small distance, something like 10 to the minus 33 centimeters. And there's very good reason to believe that the Einstein's theory will break down there. There's also good reason to believe that at very high densities, ultra high densities, more than neutron stars, also in some sense, Einstein's theories kind of break down. And so I will try to touch upon these. And one of the signatures of this breakdown is that the Einstein's equations themselves show certain pathological behavior, certain very crazy behavior. They develop what are called singularities. So I will describe that. And that's sort of a signature that at very short distances or very high densities, there must be something that replaces Einstein's theory, where you need to go beyond Einstein's description of gravity. And this is where black holes enter the picture. These are some of the most this is one of the signature predictions of Einstein's theory. It's one of the most still enigmatic ones. One way, of course, people originally came, and which we believe is the way in which these things arise in nature, is when a star dies and it's unable to sort of withstand its gravitational pull, because the matter of a very heavy star will eventually keep collapsing. Nothing can really prevent it. Subramaniam Chandrasekhar realized that all the other forces of nature, and when you form a neutron star, there is something called the Fermi degeneracy pressure. That's the last barrier that prevents matter from collapsing. But after that, things will just, if it becomes higher than the so-called Chandrasekhar mass, things end up collapsing, and they will eventually lead to these objects called black holes, whose gravitational field is so strong of the space-time and therefore is so curved that light itself cannot escape from behind a certain region of that space-time called the horizon. And this this horizon, roughly speaking, is like a spherical object whose mass is proportional to the mass of the object itself. So it can be very large for a large, massive black hole. It was first deduced, I mean, people didn't believe for a long time, for about 50 years after Einstein's theory, people didn't believe the existence of these black holes. And the first hints were in looking at a companion set of stars, so to say, in which there was one star which was losing matter to a dark kind of companion, an unseen companion. And from the calculations, it seemed as if this could only be in by a black hole. And that was one of the first hints. But quite remarkably, in the last 5 years, we have seen very direct indications from two very different sources, two different sets of measurements. We have seen direct evidence for black holes. The first is something through what are called gravitational waves, which is a prediction of Einstein's theory, like electromagnetic waves was a prediction of Maxwell's theory. There are ripples in space and time that can arise when objects move very fast and collide and so on. So this thing called LIGO, which you might have heard of, this detector, gravitational interferometric detector in the US, it detected the collision of two binary black hole system, and now it is detecting several such systems. In 2015 was the first very path-breaking detection. And quite remarkably, 4 years later, last year, a more conventional detection by something called the Event Horizon Telescope, or the EHT, which was actually a network of radio telescopes, managed to image another black hole of a very different nature. So these black holes that LIGO discovered are of tens of solar masses, whereas the Event Horizon Telescope was looking at black holes at the center of galaxies, which are of the order of 1 million solar masses. It could even be up to 1 billion solar masses. In our Milky Way, it's about 1 million solar masses. The actual image that the EHT kind of put together was of a black hole, which is a few billion solar masses. So that's something that has given us direct experimental confirmation that these remarkable objects exist in nature very abundantly, it seems nowadays. But theoretically, they are very special. They arise as very special solutions of Einstein's equations, which are highly symmetric in some ways. This is why they have a very compelling nature about them, because they are just specified by essentially a couple of numbers. If you know the mass and you know the spin or angular momentum, you basically characterize the solution completely. This is a remarkable feature of Einstein's equations, that you have these solutions which are uniquely specified once you specify these two numbers. And behind their horizon is something, this horizon I talked about, remember, from which even light cannot escape outside, which is what gives the name black hole. Behind that horizon is believed to be, at least Einstein's equations tell you, that there is something called a singularity. And the singularity is a place where the curvature, which I talked about earlier, becomes infinite. And Einstein's equations, in some sense, stop making sense because physical quantities never become infinite. So what does it mean that curvature becomes infinite? Hawking and Penrose actually showed in the late 60s, and that's what Penrose got the Nobel Prize for. Penrose started this whole program, and Hawking and Penrose showed some of the major results in this, that this presence of these singularities is something that you would always find in any, that you would generically find this in any situation where the matter is sort of moving under the gravitational force, it's essentially coming from the attractive nature of gravity that horizons will form and singularities will form. Before that, people actually thought that it's very special to these highly symmetric solutions. What Hawking and Penrose actually showed very powerfully was that this is something that can be expected in any collapse of stars, or even in the beginning, in the Big Bang, and so on. And it has nothing to do with some highly symmetric configuration. A generic star, which will not be so symmetric after all, will also produce a singularity. So you cannot avoid these singularities that Einstein's equations tell you are there. I wanted to mention here something that many people in India don't know, but the work of Hawking and Penrose used something, a result of Amal Rai Chaudhary, who taught at Presidency College and now university for many years, and in fact, I believe taught Sri Rup and so on as well. He had shown in the 50s, about a decade before Hawking and Penrose, that gravity has this sort of focusing behavior, that things, because of its attractive nature, things eventually will have to sort of, in finite time, they will kind of collapse. And this was a very important ingredient for the Hawking and Penrose's work. So it's a very seminal work, and there's the Rai-Chaudhary equation, which is still used these days. So it's a very important piece of work that has come from India and played a role in this subject. So black holes, this is why in some ways, apart from the remarkable fact that you find them now very commonly in the universe, they are a very unique theoretical laboratory for studying quantum effects in gravity. And this was in some sense pioneered by Hawking. And you have probably heard of Hawking's famous discovery that black holes radiate, what is called Hawking radiation. And what he showed was a quantum description of black holes, which people had not really studied till then. I mean, people studied, and I will come to this aspect, people studied Einstein's theory as a classical theory of the geometry of space and time. But no one had really applied quantum mechanics in any deep sense to the study of general relativity. But Hawking realized that when you consider black holes in a real, actual quantum environment, they turn out to have an effective temperature, and you can assign an entropy to them. Temperature, which is given by some beautiful formulas. That's why I've shown them here, at least for the simplest case of a spherical black hole. They are given in terms of the Planck's constant, h bar, the Newton's constant, G, that I showed you earlier, and the mass of the black hole, and there's also the speed of light, which I have suppressed, and the Boltzmann constant is also there. There's the entropy similarly is proportional to the area of the horizon. That sphere that I mentioned, whose radius is roughly proportional to the mass of the black hole, and it's again Planck's constant and Newton's constant. So this was a very kind of unnerving discovery for many people, because this completely this notion of black holes having a temperature and an entropy was very much in conflict with how they used to think of black holes in Einstein's theory, because it suggested that black holes must have some internal structure, because that's what you expect. You expect a gas of molecules to have a temperature or to have an entropy, and the entropy is a measure of the number of degrees of freedom and the different configurations that you can have inside a thermodynamical system. But why should a black hole, which I said was a unique solution of Einstein's theory, why should it have internal structure? So this was something very puzzling. And there's a second puzzle. Assuming there's an entropy, this entropy of the black holes did not behave in the right way an entropy should behave. if I have a box of molecules in it or a glass of water, the entropy in the glass of water will be proportional to the volume of the water. If I have the entropy in a room, it will be proportional to the volume of the room, the gas in a room. It is not going to be proportional to the area, the surface area of the water in the glass or the walls of the room. That never happens in any real thermodynamic system. And that has to do with the nature of the local interactions that describe all the constituents of a thermodynamic system. So the entropy never scales like area. That's a very anomalous behavior. So it's almost as if this entropy is there, but it's much fewer than what you would normally have expected. So in some ways, it's sort of almost not there. It's sort of a very small effect in some sense compared, because the volume always grows much bigger than the area does. So at first sight, it would seem as if it is much less than what you would naively think of as the entropy. So perhaps that's why Einstein's theory in some sense was not able to detect it. So it suggests that in an actual quantum theory of gravity, because you see there's Planck's constant here, the degrees of freedom are some ways fewer than in other quantum theories. And this is a hint, one of the first hints that there was something very special about black holes, which is telling us about the quantum nature of gravity. And perhaps this holds the key to some of the puzzles, because actually if you step back from black holes and just look at gravity in a quantum world, you immediately come across some puzzles which are not very easy and which have still not been really understood. Firstly, of course, physical reality we now know is indisputably, it is quantum mechanical. Or classical measurables like positions, velocities, energies, and so on. All of these only have statistical outcomes when you think of them think of them at the quantum level. There are expectation values in a particular quantum state. But now we are talking about the basic underlying dynamical objects in gravity is the metric which describes, as I said, the geometry of space and time. How can you talk of quantum fluctuations of the metric? I mean, it was already quite difficult to think of things like light as both particles and waves. And this is a nice little cartoon that I like to show, because you can see this is a very clever way in which someone has written light as a particle. If I look at it one way, you can see PARTICLE. But if you look at it another way, you can see WAVE. And that's sort of the inherent wave particle duality, which you can see here with the exclamation mark. But you can see only particle or wave. You can't see both natures at the same time. And that's, but okay, people have kind of gotten used to thinking of it, at least in a mathematical way. But it's much more difficult when you talk of the quantum fluctuations of space-time itself. In what sense is space and time a statistically average notion? It was already perhaps a big leap to make when you thought of space and time as participants in a drama, in this drama of physical events that I mentioned, the stage itself becoming a participant. But now you're asking me to now think of that stage itself as something very fuzzy, and somehow it's only a statistical notion. So if I say that, I mean, the space that I see around me is only in some sense a statistically averaged notion, or the time is just a statistical notion. What does that mean? I mean, we always think we can measure space and time as accurately as we want. How can you not do that? I mean, so it's a further kind of puzzle, and this is why we have had a lot of difficulty in reconciling Einstein's picture of gravity with quantum mechanics. And so this is the reason why the quest for quantum gravity has been a very long and very difficult one, which is still not yet, I think, realized. We haven't yet reached the fundamental, has said the last word on that, so to say. But just this quantum gravity itself, I told you a little bit about black holes and said that to understand their properties of the singularities of the black hole and maybe about their temperature and the entropy, we perhaps need a theory of quantum gravity. But we also need it, and this is sort of an aside, but just to sort of emphasize the centrality of quantum gravity. It is not only for some arcane puzzles of black holes, but it is quantum gravity is essential to understand the very birth of the universe, because the quantum fluctuations in that early period and their interactions with gravity was what gave rise to all the galaxies we see today, the inhomogeneity that we see in the sky. And these are two wonderful pictures. If you have not seen them before, the top is a picture of the cosmic microwave background, the 3-degree Kelvin radiation everywhere around us. But this plots the inhomogeneity of that radiation across the sky. The blue spots are slightly cooler than 3-degree Kelvin, about 1 part in 10 to the 5 cooler. The yellow-red parts are 1 part in 10 to the 5 hotter. This bottom one is about the inhomogeneity in the distribution of matter in the galaxy, in the universe, the various galaxies and clusters actually of galaxies which form these filament-like objects. They are not uniformly spread out in the sky. You can see there are regions where things are clustered and there are big voids in the middle. And both these inhomogeneities are actually tied up to quantum fluctuations in the very beginning of the universe right here. You can probably see it says over here. And the universe evolved from there, and these inhomogeneities kind of expanded, and now they kind of make up the structure that you see of these inhomogeneities. So it's a very remarkable story about which maybe you'll hear in the next talk more about. But another reason why quantum gravity is very essential. So let's go back to the more theoretical point of view and try to get a understanding of why, what people have tried to do in studying quantum gravity. So the first notion people had was that quantum gravity you can treat like you treat any of the other quantum forces, like electrodynamics, or the strong and weak interactions like you heard in the last talk. In fact, gravity at first sight seems very superficially analogous to electrodynamics. Someone was asking in the last lecture about electrodynamics is a gauge theory. Is gravity also a gauge theory? And in some ways, there is a superficial analogy. So let me remind you what's the case in electrodynamics. Maxwell's laws, which are kind of the analog of Einstein's equations, give a very good classical description. All the electromagnetic machinery you have around us, which generates all our electricity and powers stuff around us, is all described by Maxwell's equations, the motors and the dynamos and so on and so forth. But we know that Maxwell's, and at least people in the late 19th century, early 20th century understood that Maxwell's laws have to break down at the atomic scales. Again, they break down in two different regimes. One is at the atomic scales, because electrons are charged objects, and if they are accelerating around a proton, they will radiate and collapse. So at the atomic scale, somehow Maxwell's laws have to be superseded. There's another regime, since we talked about the limiting circumstances, another regime which is perhaps less familiar is that when electric and magnetic fields become very large, very intense, that's another place where Maxwell's laws break down and you have actually corrections to the Maxwell's equations. So anyhow, but these are now very well understood, and there's a highly successful theory of quantum electrodynamics which exists, and it predicts things to remarkable accuracy, and it is one of our triumphs of physics and in fact of human scientific endeavor because of the accuracy to which theory and prediction match. So you might first think that, yes, so this quantum electrodynamics was treated in the framework of quantum field theory, one of the other peak that I mentioned, apart from general relativity. So it was treated in the framework of quantum field theory, and there's a very successful way to describe it. So you might think you can try to quantize the gravitational field in a very similar way. It is, after all, the electromagnetic field, the basic object was a vector field, like electric field, the magnetic field, or the underlying gauge field, like vectors. But here they are slightly more complicated. They are so-called tensors. They have two indices, but that shouldn't be such a big deal, you might think. But that's where you actually realize the difference between the Maxwell's theory and Einstein's theory. And you realize the limitations of quantum field theory, because if you try to quantize the metric field in a way like you did for electrodynamics, that fails. And in some sense, though this is still not completely understood whether it's really the reason, but it's presumably because the gravitational field itself describes the whole geometry of space-time itself. And so you have to really quantize geometry, and this is very subtle. Normal quantum field theory, again, assumes that space and time are fixed and given to you, and then you quantize on the fields that live on that space-time. But when the space-time itself is sort of fluctuating, you don't know how to quantize it. We still haven't learned how to quantize it, and perhaps it's not even directly possible in that way. And in some ways, I think this failure of quantum field theory is exemplified by these puzzles that I mentioned in black holes. The fact that the entropy is like the area and not like the volume. In any quantum field theory that you compute, the entropy has to come out like the volume. So you know that somehow gravity is not quite described by a quantum field theory. So the Hawking's calculation in some ways is one of the sharpest ways to kind of pose that. So there's clearly, gravity has to be treated differently at the quantum level than any of the other forces. I think by now this is abundantly clear. So in the last minutes of this talk, I want to tell you a little bit about the more radical thoughts that people have had in quantizing gravity. And string theory is, I think, one of the frameworks which has been most successful, has gone furthest along in that road, and I think is, of course, still far from answering everything there, but has already taught us many new things about gravity. And I'll try to give you a flavor of that in these last few minutes. So in some ways, string theory can be viewed as some modification of quantum field theory, which is sort of what I like to call conservatively radical. It's not like totally radical like Einstein's theory. So on, it's a conservative, it's like how a person who wants to make small but important changes tries to do things. I guess like most politicians who are who don't want to sort of rock the boat. So, any case, string theory is, as its name suggests, about the quantum dynamics of extended objects, like closed strings like this, like rubber bands, or open strings, which are like some pieces of thread. It's a very, but when you try to study the quantum dynamics of these extended objects, it's a very intricate, a very kind of a delicate framework. It is not very easy to quantize them without creating some internal inconsistencies. So it's much more highly constrained than actually even quantum field theory is. There are multitudes of quantum field theory, one of which happens to be realized in the description of electroweak symmetry and or quantum chromodynamics, the strong interactions. There are many others that condensed matter physicists use to describe various exotic systems of theirs. So there are multitudes of these quantum field theories, but string theory is somehow much more constrained. And once again, because of the presence of gravity, which comes kind of naturally out of the box, so to say. It is sort of built into the framework. And therefore, it showed some very early promise in addressing some of the difficulties, what physicists call renormalizability of quantum field, of quantum gravity. This was sort of, I think string theory was able to address this, and this is why people became found it very promising. But in some sense, it hadn't really addressed the notion of what is quantum space-time. But in the last couple of decades, that has sort of changed. And in some ways, the whole internal consistency of the theory really pushed you to a very striking conclusion, because what arose was a very precise proposal for how a large class of spacetimes, which are described by Einstein's theory, can behave at the quantum level. And the surprising answer was that in these cases, quantum gravity turns out to be described by a quantum field theory. But I just told you a little while ago that it is by now abundantly clear that quantum gravity cannot be described by a quantum field theory. So there's a twist in this statement. It is that this is described by a quantum field theory in one lower dimension. And this happens in a very unusual, very kind of almost unthinkable way. And this was the proposal by the Argentinian physicist Juan Maldacena for the quantum behavior of a class of spacetimes called anti de Sitter spacetimes. And these are the exact details need not bother you. It's a spacetime which has a sort of a hyperbolic-like geometry. So you can think of the geometry as essentially like a solid cylinder. So it's a solid, so the interior of the cylinder is also part of the space-time, but there's a boundary of that space-time, which is the surface of the cylinder. So if I think of a three-dimensional cylinder like this, its boundary is a two-dimensional surface, what you normally call the cylinder, the surface of the solid cylinder. And the statement is that the quantum behavior of this hyperbolic or anti-de Sitter spacetime in this case, in the picture, 3 dimensions, is described by a quantum field theory that lives on the boundary of this spacetime, this 2-dimensional boundary of this spacetime, or similarly in higher dimensions, which of course I can't draw. So this quantum field theory is not a quantization of this metric inside the spacetime. That's what was creating all the problems earlier. But it is a quantization of fields which live on the boundary, which are in some sense generalizations of electromagnetism, more like the quantum chromodynamics theories that you heard about in the previous talk. And there is, in these cases, a very precise dictionary between things you can compute on the boundary in the quantum field theory that lives on this one lower dimensional boundary with observables in the higher dimensional space-time. Now, I must caution you that this is known for a special class of these spacetimes. as I said, these anti-de Sitter spacetimes. It's a very large class, and you have many theories in many dimensions, and this has been studied in lots of cases. But they typically have some other features which we don't see yet in the real world, like supersymmetry in many cases, though there are cases without supersymmetry as well. But it's understood in some certain theoretical, in a certain class of quantum field theories and certain class of spacetimes. But it is such a large class that it makes you feel and gives you a sense that this is actually a universal phenomenon, that this thing actually is it's telling you a more general fact about quantum gravity. And that fact is that in some sense, quantum gravity is what is called holographic, namely like a hologram captures information about one lower dimension. Everything about the quantum anti-de Sitter spacetime is encoded in that one lower dimensional quantum field theory, and this is some kind of a cartoon of that. And there are, in some ways, it's the bits of this one lower dimensional holographic quantum field theory that is capturing everything about the higher dimensional spacetime. Once again, I must caution you that this is a picture which we understand to a large extent in a large class of theories and so on, and therefore it kind of suggests this sort of a picture, but we are yet we still have many things still to understand about whether this is really true. But one thing this kind of holographic picture immediately kind of tells you is that about the physics of at least black holes in these anti-de Sitter-like spacetimes. It can address the puzzles that I raised, the ones that Hawking and so on described. It can address those puzzles because the boundary quantum field theory captures the physics of those black holes very precisely. In fact, you can identify a state in the quantum field theory which corresponds to that black hole inside the anti-de Sitter spacetime. It is a state which is at a finite temperature. In quantum field theory, you can heat up states and have them at a certain temperature. In fact, you can have states at the Hawking temperature, and that describes the black hole geometry. Moreover, the quantum field theory gives a description, captures all the micro states, the individual configurations that give rise to the Bekenstein-Hawking entropy formula, the one that I wrote down some slides ago. And moreover, it tells you very naturally why it's proportional to the area and not the volume, because the quantum field theory is, as I said, the quantum field theory is always extensive, the entropy is always extensive, but now it's in one lower dimension, so it corresponds to the entropy of like a one lower dimensional theory, which is, so the area behavior, which was a hint from black holes that something unusual is happening in quantum gravity, very much suggests that this holographic picture is ultimately true for the quantum description of gravity. So I've sort of come to the end of my time and the talk. So let's just stand back. What have we learned from the original quest that I started with? So as I said, we still have yet to fully understand what quantum gravity is, but it's a very challenging and remarkable puzzle, and tells you that gravity is somehow at a very different footing from other forces, and quantum gravity probably has this very unusual holographic description, which allows you to, at least in some cases, understand the microscopic origin of this entropy that Hawking and actually independently Bekenstein proposed. And this notion that seems to arise from this holographic picture is that space and time, as I said, at the quantum level, in what way are they statistically averaged, or how are they fluctuating? It's in some sense same way as perhaps our notion of space and time as some continuum is a bit like our view of water as a continuous fluid, which we normally described by some fluid equations, which are continuous equations. So space and time also perhaps seem to us like that, but really we understand that water at the microscopic level is not a continuous fluid. It is made of discrete atoms. And in some sense, this is perhaps what the space-time is, except that it's these discrete description is sort of on the boundary in some captured in some holographic way. But we need to, so to say, decode this hologram, understand it better in different cases. Is this how quantum space-time always behaves? So, but in the meanwhile, this connection has uncovered very striking new facts about quantum field theories as well, and that's kind of a subject of a whole new talk, because it tells you this dictionary between gravity and theories of normal quantum field theories, which are of interest to people across many domains, particle physics being one, but condensed matter physics, astrophysics, and plasma physics, and so on. And many of them want to have tried to use this to learn things about quantum field theories when they're strongly interacting. And in some ways, people ask often about the experimental status of string theory. We are still far from there, because we are talking about regimes which are very difficult to access experimentally. But nevertheless, it's what we have here is something quite non-trivial and falsifiable, because we are making predictions about theories which predate string theory. Quantum field theory and general relativity were these two peaks of 20th century physics that originated in the 1920s, more than around 100 years ago. And they come much before string theory, which emerged in the 60s and 70s. And these are very well tested and validated theories in their respective domains. And we are learning new things, new facts about them, which can be actually falsified, and which shows that string theory is remarkably kind of rich and is able to tell you new things about things that existed independent of string theory. But understanding this underlying mechanism for this connection between quantum field theory and general relativity will give us new insights into quantum field theory also, and that's powerful in many real world contexts. So what I would like to leave you with is this thing that these two different peaks of 20th century physics, which for a long part of the 20th century seemed like very disconnected peaks sitting on opposite ends of the Himalayas, so to say, you will actually see them linked finally together. So I hope to see some of you on this trek. Thank you very much.
Thank you very much, Professor Rajesh. Yeah, I really sincerely hope that people will be on the track, and they will really reach some of the peaks one day. And we are already running behind the schedule, but I would like to take a few questions very quickly. If you have time, may I?
Yeah, I have I have maybe 5-10 minutes. I can.
Sure, only 5 minutes, because he is waiting eagerly to speak, so I could see him.
Yeah.
So let us take 2-3 questions there. I mean, one is very trivial, but okay, let us take it. So one person, Devojyoti Vallabh, is asking, what happens to the quarks in a dying star when they are crushed together? Since they are confined, what will happen to them? This is the question, basically. He has written in a different language. So can you please, I will go one by one.
Yeah. Yeah, so that's a very interesting question. I mean, people believe that at very high densities, actually, quarks can be liberated. And this is something that people are still studying, high density QCD. So we don't completely understand the phase diagram because we still don't have direct ways to measure it. But I mean, people do talk of things called quark stars. I mean, neutron stars, beyond neutron stars, you can have things which are more like quark stars. But it's still a little speculative. People have to kind of deduce them through signatures when stars send out some, depending on the behavior, surface behavior of the star, or from its radiation, you have to kind of deduce indirectly and try to fit it to this picture. But that's essentially the that's I mean, I think that's the best we know at this moment about what happens to stars when they are crushed and the quarks are kind of perhaps liberated.
So in that high density, what will happen? That is still unknown. Devajyoti, we wish that it will unfold in near future. The second question is that whether symmetry plays a role in the fact that the electrons and protons never collide, even they have an attractive force between them.
No, I don't understand. Electrons and protons do collide.
Yeah, why it should not collide? But his question is, Nikhilesh, do you understand what you are? What you meant to say? Actually, I don't understand your question. Though I'm just reading out from your chat. Nikhilesh, are you there?
Yes, ma'am.
Yeah,
My
can you
question is that,
yeah.
My question is that why don't electrons and protons collide even though they have attractive force between each other?
Who told you that?
You can scatter. In principle, you can scatter electrons of protons, and they will scatter. Sometimes they can form bound states, of course, when you come too close. If the energies are low, then of course the electron will get trapped by the proton and will form a hydrogen atom. But you can scatter electron off a proton, and people do in fact study the inside of a proton that way very often. I mean, through what is called deep inelastic scattering. They study the insides of the protons because they can kind of probe the quark structure inside the proton through these scatterings.
So we have talked about the bound state where electron revolves around the protons of the nucleus, but why don't they ever collide?
I mean, it depends on what you mean by collision. If you really mean that the electron and the proton fuse together, that's very difficult to achieve because you have to kind of aim it exactly right. But in principle, that can happen. And there are other situations also where what's called, electron capture happens. And a proton can kind of capture an electron, and you can have a neutron or something produced. But in a scattering experiment, it is very difficult to make the thing fuse. What will typically happen is that they will kind of they will bounce off each other. They will because the energies are so high that there is too little. You have to kind of push it at just the right amount of energy so that it can be captured. It's like if I throw a ball at a very high speed, it's more likely to get deflected, right?
So I meant to say it's like if I have two magnets in a box and I close it and shake it, they are attracted to each other and they come close and get attracted to each other. In a similar way, can't it done?
Yeah, like I said, in a certain, so you have to arrange things such that there's no relative angular momentum, so to say. Electrons and protons are very tiny objects. Magnets are very macroscopic, big objects. So their cross section, so to say, is much higher. If I have two large magnets, even if a small part of it overlaps with each other, they kind of capture each other. But protons and neutrons are more like point-like objects. So you need to have their impact parameter, so to say, very small so that they can actually just collide and be captured. But it does happen. In fact, in the lowest orbit of the hydrogen atom, sometimes there is a chance for an electron capture. There is a probability for that to happen, but it's a small number because of the fact that they are very small objects, point-like objects almost.
I hope you have got an answer to your query. The next question is asked by Shramana, who is putting question on naked singularities. If do they, I mean, why do they say that naked singularities do not exist? What is the problem related to the naked singularity? And she also asks that since the Planck length is very small, is that the reason we think that the space and time both are quantized? This is the question by Shramana Ghosh.
Okay, so the first question about the naked singularities, it's still a conjecture in the sense that there's something called the cosmic censorship conjecture, which tells you that at least with very general initial conditions, any matter, when it kind of collapses and forms a horizon, forms a singularity, there will be always a horizon near it. There is good reason to believe that from the general arguments that Penrose and others produced to why singularities are generic, to believe that these so-called trapped surfaces or horizons will form. So but it's still a conjecture. No one has proved it. And indeed, there you can arrange initial conditions in a very special way such that you can have a singularity without having a horizon. So that's also possible. In fact, theoretically, you can. It's not impossible. There's no law of nature that prevents it. It's just that it's very unlikely to happen. So you have to, so in a generic situation, like in a star or this thing collapsing, you will very likely form a horizon, and it's only the singularity of the black hole will be behind that horizon. But so that's the first part. About the second part of the question, that was the second part was about the Planck scale, right? So the Planck scale, of course, it being very small, is why you do not, at least in all our experiments so far, I mean, we have gone up to maybe, I don't know, 10 to the minus, I think it's about 10 to the minus 20 centimeters or something like that, 10 to the minus 18 or 20 centimeters, the shortest distance we have gone to. At those distances, definitely we have not seen any structure of quantized space and time, but because this is still 10 to 13 orders of magnitude smaller, the Planck scale, so you would need to probably find other signatures of that. So yes, in that sense, from an experimental point of view, it is that's the reason why you do not see the quantum structure of space and time in anything that we have found so far. It's a bit like water also. If you're a person who is operating at a centimeter scale, the atomic structure of water is visible only at the angstrom scale. So you so you don't, there's several orders of magnitude separating you and the discrete nature of water. So you will only see it if you develop more powerful tools or microscopes or whatever it is. And that's what, of course, we have done with respect to atoms, but we have yet to do with respect to space and time.
Yeah, I think this satisfies Shramana. And next question I will keep reserved for Dr. Rishi, because it's on dark energy, dark matter. So because you have other engagements.
Yeah.
Thank you so much, Rajesh, for being here. Being a director, it is very difficult to spare time, I understand, but you could manage it for us. And I'm so thankful and grateful that you accepted our invitation and you could make it to this session. And it was really nice, like that people could hear you in this occasion. And if some specific questions are there coming up from the participants, I will forward them to you.
Okay.
And yeah, so
Sir, I have.
I really thank you for being here.
Yeah,
Your question will be answered by Dr.
Ma'am, can I ask one question?
No, not now. Your question is reserved for Dr. Khatri. Don't worry. He will get your answer.
Yeah.
So,
So enjoy the rest of your talks, especially the
yeah,
ones
yeah.
by
So,